In this session, we will be discussing about the quantitative aspect of electrolysis, that is the amount of substance deposited or the amount of gas liberated. Both the things can happen. In your previous session, we have seen wherein gas can be even liberated at an electrode or a substance can be even deposited. So, the relationship between the mass of the substance liberated or deposited with the current passed is called as your quantitative aspect of electrolysis. So, it is a relationship between the mass of substance deposited or liberated with the electric current passed. So this relationship is called as your quantitative aspect of electrolysis. So about this relationship of mass of a substance deposited with the electric current was hugely studied by a person called as Michael Faraday. Hence, he put forth two important laws of electrochemistry, that is your Faraday's first law of electrolysis as well as Faraday's second law of electrolysis. Both the laws are interconnected to one another. So, let us see the first Faraday's law, that is Faraday's law of first law of Faraday's electrolysis as well as second law of Faraday. So, what does it tell and what is the relationship we will be going to see now. So, Faraday's first law of electrolysis, what does it tell? So, it is purely a relationship between the mass of substance deposited versus the amount of charge that has been flown through the electrolyte. So, Faraday's first law tells that the amount of substance liberated or deposited, that is W. So, here W means it is the amount of substance or mass of substance deposited or liberated, if it a gas, is directly proportional to Q. What is this Q? Q is the amount of charge flown through the electrolyte. So, according to Faraday, the amount of substance deposited or liberated at an electrode is directly proportional to the charge flown through the electrolyte. So, here W is the amount of substance deposited or liberated at an electrode. Q is the amount of charge flown through the electrolyte. So, according to Faraday, these both are directly proportional, that is how much amount of substance is deposited or liberated is directly proportional to the amount of charge flown through the electrolyte. This proportionality, I can remove it using a proportionality constant, that is W is equal to Z into Q. So, here Z is your proportionality constant, which is also called as electrochemical equivalence. So, Z is your proportionality constant which is called as ECE, that is nothing but electrochemical equivalence. It's very important. We'll be discussing more detailedly about this Z in your future sessions. So, here W is equal to Z into Q. W is amount of substance deposited or liberated, Z is your electrochemical equivalence and Q is your amount of charge flow. We know that I, what is I? It's current, electric current. So, the definition of electric current is nothing but it is the charge flown per time, that is it is the charge flown per unit time is called as your electric current. So, I can write I as, that is electric current as I is equal to Q divided by T. So, what is Q? Q is your charge flown per unit time is called as your current, electric current. So electric current is the amount of charge flown per unit time. So therefore I can write it as Q is equal to I into T. That is, charge flown is equal to I, electric current, it should be in amperes, and time in per seconds. So Q is equal to I into T. I is the current flown in amperes, very important, it is in amperes, and T is time in seconds. So therefore Q is equal to I into T. Q is charge, amount of charge flow. Therefore the equation becomes, say this, I'll take this as equation 1, I'll take this as equation 2. So upon substituting this Q value in equation 1, so Q value or Q in equation 1, what does this become? In equation 1, very simple, W is equal to Z into I into T. So this is your mathematical form of your first law of electrolysis, that is Faraday's first law of electrolysis, that is W. What is W? It's the amount of substance deposited. What is Z? It is the electrochemical equivalence. We'll simply call it as ECE. I, it is the amount of electric current passed in amperes, very important. T is your time in seconds. So this is your mathematical form of Faraday's first law. So now we'll be discussing about the second law of Faraday, that is Faraday's second law of electrolysis. So this second law tells about what is the amount of substance deposited if a fixed amount of electric current, that is if a fixed amount of charges is flown through different substances. So I have taken an illustration to show you that there are two cells, cell 1, cell 2. So the cell 1 wherein 2 electrodes are dipped in NaCl solution, the cell 2 wherein the 2 electrodes are dipped in copper sulfate solution, which is connected to an electric current, electric supply, and same amount of electricity is passed through both the substances, that is both the cells, so cell 1 and cell 2. So when both the cells have same amount of electric current passed through, we can observe that the amount of substance deposited, that is amount of sodium deposited and amount of copper sulfate deposited at the respective electrodes, at their respective electrodes is equal to, say sodium is equal to 23 grams, sodium is equal to 23 grams and copper is equal to 31.9 gram approximately, 31.9 grams. So when same amount of electric current is passed, the amount of substance, that is sodium and copper, deposited at their respective electrodes is equal to 23 grams and 31.9 grams, which means that the amount of substance deposited when some fixed amount of electric current is passed through different substances, it is equal to their equivalent weights. What is this? These are the equivalent weights of the substance. Equivalent weights of the respective substance, which means that the amount of substance, any amount of substance deposited at their respective electrodes when certain fixed amount of electric current is passed, it is directly proportional to their equivalent mass. So E is your equivalent mass. So E is your equivalent mass. So this is your E. So according to Faraday's second law, it states that when a certain fixed amount of charge is flown through a substance, through an electrolyte, the amount of substance deposited W, it is directly proportional to your equivalent mass of their substance, which means that I can write this as W1 by W2, it is directly proportional to, or I can tell it as it is equal to E1 by E2. So what is this E1? E1 is the equivalent weight of one compound and E2 is the equivalent weight of other compound. So this is about your Faraday's second law. So it tells that, very simple, the amount of substance deposited at any electrode when a fixed amount of electric current is passed or charge is passed is equal to its equivalent weight. Now we know what is W from your previous law, that is first Faraday's law. We know that W is equal to Q into Z. Sorry, Q into Z. What is Q? It's your charge flown. What is Z? It's your electrochemical equivalence. So therefore I can write this equation as Z into Q, Z1 into Q divided by Z2 into Q is equal to E1 by E2. Therefore I can tell that your equivalence, electrochemical equivalence is equal to your equivalent weight of a substance. So Z, your electrochemical equivalence, it is equal to your E, that is your electrochemical equivalence, which is nothing but I can write it as Z is equal to E by F. E by F. Let us see what is this F in the further discussion. So remember Z, your electrochemical equivalence, Z is equal to equivalent weight by Faraday, that is your F. What is F? We will be seeing now. So we have seen that the amount of substance deposited by your sodium chloride solution and copper sulfate solution, it is equal to its equivalent weight. So remember also equivalent weight is equal to the molecular mass of the substance or molar mass of the substance divided by X. Here X may be valency. It can be charge. It can be charge of any, if it is an ion, it can be a charge, or even it can be number of electron transferred. Equivalent weight of any substance is equal to your molar mass divided by X. X is valency or charge or number of electrons transferred if it is a redox reaction. So now let us see how is this sodium getting deposited at the respective electrodes. Say sodium, NaCl, it is in the form of NaCl, which means sodium is in the form of Na plus, which accepts an electron to get deposited as Na. This is your solid, this is your aqueous form. Which means that to reduce 1 mole of sodium ions into 1 mole of sodium atoms or solid form, it requires 1 mole of electrons. That is, you have to pass charge that is equal to 1 mole of electrons to get deposited your sodium, aqueous sodium into 1 mole of aqueous sodium into your solid sodium. Now the question is, what is the charge on this? What is the charge on this 1 mole of electron? That is, how much charge should be flown to make this 1 mole of sodium ions into 1 mole of sodium atoms, that is solid. So what is the charge? Very simple, 1 mole of electrons is equal to 6.022 into 10 to the power of 23 electrons, which is nothing but your Avogadro number, into charge of 1 electron, The charge of 1 electron would be 1.6 into 10 to the power of 1.6 into 10 to the power of minus 19 coulombs. It's the charge of 1 electron. So 1 mole, it is equal to Avogadro number of electrons into charge of 1 electron, which will be equal to 96,500 coulombs. So this is the charge of 1 mole of electrons, which is a constant. You call it as Faraday's constant. That is represented by capital F. This is your F here, which is called as Faraday's constant. It is equal to 96,500 coulombs. What is this 96,500 coulombs? It is the total charge carried by 1 mole of electrons. So that's about your Faraday's constant. So here equivalence, that is electrochemical equivalence, it is equal to the equivalent weight of the substance divided by Faraday. What is Faraday? It's your electrochemical constant, it's your charge on 1 mole of electrons. So that is equal to 96,500 coulombs. So summarizing your Faraday's first law and second law, you will be having one equation, that is, from first law we have studied that W is equal to Z into Q. So what is Z? Electrochemical equivalence. Q is the charge flown through the electrolyte. What is W? It is the mass of substance or the mass of the gas liberated at the respective electrodes. So therefore, W is equal to, we have just known that Z is equal to E by F. What is E? E is your equivalent mass. What is F? F is the Faraday's constant, that is equal to 96,500 coulombs. So Z is E by F into Q. W is equal to, what is E? E is molecular mass by X, where X is valency, charge or number of electrons transferred if it is a redox reaction. So E is nothing but the molar mass divided by X into 1 by F. F is Faraday's constant into Q. Q can be written as I into T. We have already derived in your previous session, that is previous Faraday's law. So therefore, final equation can be W is equal to molar mass divided by X into 1 by F into I. What is I? I is current in amperes into T. So what is T? T is time in seconds. So this is the overall equation when you sum up your Faraday's first law as well as Faraday's second law. Summarizing, Faraday's first law, it tells that amount of substance deposited or liberated at respective electrodes, it is equal to the amount of charge flown through the electrolyte. Faraday's second law, it tells that the amount of substance deposited at respective electrode when the current is constant, that is when the charge flown is constant, it is equal to its equivalent weight of the respective substance. So summarizing it, you get this equation, one whole equation which summarizes both the laws, that is Faraday's first law as well as Faraday's second law. So in the next session, we will be discussing about the problems based on this Faraday's first law and Faraday's second law. Faraday's first law statement is very important. You will be getting for 1 mark, state Faraday's first law, as well as sometimes the problems are also important for 1 mark problems. So Faraday's first law and second law has their problems in your second PUC annual exams. So now we will be having the numericals of based on Faraday's first law and second law. A very important type of problem for your Faraday's first law and second law, wherein you have to calculate the amount of charge in terms of coulomb. They have given you it is charge, which means you have to keep the answer in terms of coulombs. Charge required to have the following reductions. Reduction means addition of electrons. So first problem, let us take aluminium 3 plus to aluminium. 3 plus means it is short of 3 electrons, which means you require Al3 plus 3 moles of electrons to get this aluminium. So in order to reduce 1 mole of aluminium 3 plus, you require 3 moles of electrons to get your aluminium, that is reduced form of your aluminium. So 3 moles of electrons, which means its charge, it is equal to, its charge is equal to 3 Faraday. 3 Faraday, that is 1 Faraday is the amount of, that is the charge on 1 mole of electrons. So 3 moles means 3 into 1 Faraday, that is Faraday is the amount of charge on 1 mole of electrons, which means that is equal to 3 into 96,500 coulombs. So remember, Faraday is charge on 1 mole of electrons. So 3 into 1 Faraday. So that is 3 into 96,500 coulombs. So that is equal to, the answer would be 2,89,500 coulombs of charge. So you require 2,89,500 coulombs of charge to reduce aluminium 3 plus 1 mole of aluminium 3 plus to aluminium. That is nothing but simply telling it is 3 Faraday. So remember, how many moles of electrons is required? Those many Faradays of electric current is required, charge is required. So multiply it with the respective coulombs, that is 96,500 coulombs. You get the total amount of charge required for the following reduction. So what is the oxidation of Mn here? Say X plus 4 into minus 2 is equal to minus 1. minus 1 is the total charge, minus 2 is the oxidation state of oxygen. So X will be equal to minus 1 plus 8. So X will be equal to plus 7. So here the oxidation state of manganese is plus 7. So plus 7 to plus 2. How many electrons? Plus 7 means short of 5 electrons, plus 2 means short of 2 electrons. So 7 to 2 means it is short of 5 electrons. 5 electrons, which means that MnO4 minus, this is plus 7 oxidation state, plus 5 moles of electrons will reduce it to Mn plus 2. So you require how many moles of electrons to reduce this species? It requires 5 moles of electrons. So what is the charge on this? The charge is equal to, charge on 5 moles of electrons is equal to 5 into charge of 1 electron, sorry, 1 mole of electron is Faraday. So 5 Faraday of charge is required, which is equal to 5 into, what is Faraday? It is 96,500 coulombs. So this is will be equal to 4,82,500 coulombs. So the amount of charge in coulombs, it is asked in charge, so you have to keep it in coulombs. So amount of charges that is required to reduce Mn plus 7 to Mn plus 2 is 4,82,500 coulombs. So 5 moles of electrons is required. Charge of 1 mole is 96,500 coulombs. So 5 into 96,500 coulombs, it is equal to 4,82,500 coulombs. So Cr2O7 2 minus 2 Cr3 plus. Here what is the oxidation state here? 2 into X plus 7 into minus 2 is equal to minus 2. So 2X is equal to minus 2 plus 14. X is equal to plus 12 divided by 6, that is equal to plus 12 divided by 2, which is equal to plus 6. So oxidation state here it is plus 6. So plus 6 to plus 3. How many electrons? Plus 6 is short of 6 electrons, plus 3 is short of 3 electrons. So the number of electrons required to reduce is 3 electrons. So I can write it as Cr2O7 2 minus plus 3 electrons for 1 mole of chromium. So 2 moles of chromium requires 3 into 2. So 6 electrons. This give rise to 2 moles of 2 Cr3 plus. So 6 moles for 2 moles. So if you want to calculate it for 1 mole, it is 3 electrons. Since chromium is 2, you have to require 2 3s are 6 moles of electrons. So 6 moles of electrons, it is equal to 6 into Faraday. What is F? F is the charge on 1 mole of electrons, that is equal to 6 into 96,500 coulombs, that is equal to 5,79,000 coulombs for 2 moles of chromium. 2 moles of chromium. If it is for 1 mole, divided by 2, you get your answer for 1 mole. Since the equation is for balance for 2 moles, I have calculated it for 2 moles. So 2 moles of chromium, 6 plus requires 6 moles of electrons to get reduced into 3 plus. As a result, this is the amount of charge required for reducing 2 moles of chromium. If the question is for 1 mole, divide it by 2. Next, let us see the second problem, that is a solution of copper sulfate, aqueous solution of copper sulfate is electrolyzed for 10 minutes with 1.5 amperes of current. It is the amount of current passed. What is the mass of copper deposited at the cathode? That is the respective electrode. You have to calculate what is the mass of the copper deposited. First, let us see what are the things given and what should you calculate. So let us take the given. What are given in this problem? So a solution of copper sulfate is electrolyzed for 10 minutes. So T is given, time 10 minutes with a current of 1.5 amperes. So I is given, I is 1.5 amperes of current. What is the mass of the copper deposited? That is, you have to calculate what is W. You have to calculate what is W. So let us have the formula, that is W is equal to Z into Q. Z into Q. So since these factors are not given, I will have the substituted formula, that is W is equal to Z is E divided by X into 1 by F into I into T. So I is given, it is 1.5 amperes and I should be in amperes, it is correct. T is given in minutes, convert it into seconds, that is 10 minutes into 60, it will be converted into seconds. So E, equivalent weight of copper, so sorry, here it is molar mass, molecular mass by X. So the molecular mass of copper, it is equal to 63.45 grams. So molecular mass of copper is 63.45 grams. Since in copper sulfate, copper is in +2 state, so the equivalent weight will be divided by 2, that is X is equal to the charge on copper, that is equal to 2. So X is charge of copper, as I have told you, X can be either charge or it can be the valency or it can be the number of electrons transferred. So X here it is charge, it is equal to 2. Then Faraday, we know Faraday is a constant, it is equal to 96,500 coulombs. So everything I have got it now, just substitute it. So W is equal to molar mass of copper 63.45 grams divided by 2, 2 is X, the charge on copper, +2 into 1 by 96,500 coulombs into current in amperes, that is 1.5 amperes, into time in seconds, 10 minutes is given, so 10 minutes into 60. This is for conversion of time in seconds. So 63.45, the molecular mass of copper, divided by 2, it is nothing but X, that is the charge on copper, 1 divided by 96,500, Faraday's constant, 1.5 amperes, time in seconds, 10 into 60. So therefore, after substituting this, the mass of copper deposited at the respective electrode will be 0.2961 gram. 2961 gram. So 0.2961 gram of copper will be deposited at the cathode. So this is how you do by substituting your formula, that is W is equal to Z into Q, where Z is also not given, Q is also not given. Hence, I will be having this formula, as I have told you in your previous session, it is a combination of both Faraday's first law and second law. So the next problem will be, calculate the amount of charge required to deposit 40 grams of aluminium from Al2O3. Here we will not be using your authentic formula. I will be telling what is the shortcut to solve this problem, which will be helpful for your competitive exams. So previous formula, that is your Faraday's first law and second law combined formula, can also be used, but here I will be showing you shortcut wherein you can calculate what is the amount of charge required to deposit this Mn amount. It is a shortcut and it is not a formula based answer. First, let us see what is the transformation, what is the reduction happening. You can observe here it is from Al2O3, that is, what is the oxidation state here? It is +3 to Al. So +3 to 0. So how many moles of electrons is required? We have discussed in the first example itself, it is 3 moles of electrons is required. So therefore 1 mole of aluminium +3 to aluminium reduction requires 3 moles of electrons. 3 moles of electrons, which deposits how many grams of aluminium? Very simple, it deposits 1 mole of aluminium. So what is the molecular mass of aluminium? So that is 1 mole of aluminium, its molecular mass, it would be 26.98 grams. So To reduce 1 mole of aluminium 3 plus to aluminium, it requires 3 moles of electrons, which produces 26.98 grams of aluminium deposited. So 3 moles of electrons deposits 26.98 grams of aluminium. So how much is the aluminium given? You have seen this, 40 grams of aluminium should be deposited. So therefore 40 grams of aluminium deposition requires how many moles of electrons? If I get how many moles of electrons into Faraday, you get your charge. That's the question asked. That is, calculate the amount of charge required. So what is this? This is equal to 40 into 3 divided by 26.98. That will be equal to 4.460 moles of electrons. So these many moles of electrons is required. Therefore 4.460 moles of electrons into Faraday, that is equal to 4.460 into 96,500 coulombs, that is equal to 4,29,200 coulombs. 206 coulombs. 206 coulombs of charge. So this much amount of charge is required to deposit 40 grams of aluminium from aluminium oxide. So very simple, 1 mole from your standard equation here, you came to know that 1 mole of aluminium reduction requires 3 moles of electrons, which deposits 26.98, approximately 27, you can take it as 27 grams of aluminium deposited. So 40 grams of aluminium require how many moles of electrons? So those many moles of electrons you get, multiply by Faraday. Faraday is the charge on 1 mole of electrons, multiply by 96,500 coulombs, it's a constant, you get the amount of charge deposited from the, that is amount of charge required to deposit 40 grams of aluminium from aluminium oxide. The next problem will be, calculate the number of chlorine molecules. Remember, you have to calculate here the number of chlorine molecules liberated. So it is a gas liberated upon electrolysis of liquid NaCl, that is your molten NaCl, with a current of 1 ampere for 15 minutes. So you have to calculate the number of chlorine molecules. So directly we do not have any formula to calculate this chlorine molecule. As a result, I will be first determining what is the mass of chlorine deposited or liberated, upon which I can calculate from the mass into Avogadro number, I can calculate the number of molecules of gas liberated. So first it is required to calculate the mass of chlorine deposited upon electrolysis of liquid NaCl, that is nothing but your molten NaCl. So what is given? If I take what is given here, given is I, which is equal to 1 ampere, it is an ampere itself, time, it is equal to 15 minutes, which I have to convert into seconds. What I have to calculate? W I have to calculate. Also I have to calculate number of molecules of chlorine. N, number of molecules of chlorine also I have to calculate. So what is the formula? We know W is equal to Z into Q, that is W is equal to M molecular mass divided by X into 1 by F into I into T, which fetches me what is the mass of chlorine gas liberated. So what is the molecular mass of chlorine? Molecular mass of chlorine is equal to 70.5 grams, 70.5 grams, sorry 70.9 grams. So that is equal to X. So the valency of chlorine, that is the atomicity of chlorine, it is equal to 2. So X, it is equal to 2. So that is equal to 70.9 divided by 2 into 1 by 96,500 coulombs into I in amperes, it is 1 ampere. So 1.0 into time in seconds, so 15 into 60. So therefore W will be equal to the amount of chlorine gas liberated will be equal to 0.3306 grams. This is your W, that is amount of chlorine gas liberated. Now, using this, I can calculate the molecules, number of molecules of chlorine gas liberated. So, let us see how to do it. .9 grams of chlorine gas is equal to 6.022 into 10 to the power of 23 molecules. This is Avogadro number. This is equal to 1 mole. 1 mole of any substance, it is equal to its molecular mass. It is equal to the Avogadro number of molecules. So, therefore, 1 mole of chlorine gas is equal to 70.9 grams of chlorine, which is equal to 6.022 into 10 to the power of 23 molecules, Avogadro's constant. Therefore, we have calculated W here, it is equal to 0.3306 grams. So, therefore, 0.3306 grams of, 6 grams of chlorine gas has how many molecules? That is equal to 0.3306 into 6.022 into 10 to the power of 23 divided by 70.9 grams. That is equal to 70.9, that is equal to 2.808 into 10 to the power of 21 molecules. So, this is your number of molecules of chlorine gas. Molecules. So, this is 2.808 into 10 to the power of 21 molecules is liberated when you pass a current of 1 ampere for 15 minutes through your liquid NaCl. You get this amount of molecules, that is 2.0808 into 10 to the power of 21 molecules.